Yeah, thank you for the introduction. I am SCA and I'm a PhD student at the University of Waterloo in Canada, and I'm going to talk about the work surface only dynamic deformables using boundary element method. So in our method, we aim to simulate dynamically deforming objects based on elastodynamic simulation in a surface only manner for the first time in computer graphics. And it requires no internal volume discretization and no computation over the interior domain of the volumetric domain. So popular methods in animation, such as FEM, require the costly and complex volumetric meshing operation first, which discretizes the interior of the input surface mesh, and then constructs an equation for each tetrahedron. And also other existing methods also require at least computation over the volume. On the other hand, our method is based on boundary element method, or shortly BEM, which constructs an equation for the relation between each vertex and all vertices on surface. Here's a demonstration of a method. We drop elastodynamic fish into the rigid bowl. And let me emphasize again that our work uses surface mesh as input and for computation. So it's really truly surface only method. And as our method simulates elastodynamics rather than elastostatics, we can see the fish tail moving dynamically in this video. BEM has been applied to computer graphics applications for several purposes, including elastostatics, fracture, and 3D fluid simulation. However, our work applies BEM to elastodynamic simulation problem for the first time. Let me describe the intuition behind the surface-only elasticity simulation using BEM. In our method, we assume that the input geometry is a surface triangle mesh, more precisely, and then we use the linear elasticity assumption. And the problem here is to find displacement of vertices on surface, given traction or force applied on surface. Let's say you want to find the displacement of this red vertex. Then there is an elastic wave propagating from this yellow vertex, for example. So the displacement and the traction at the yellow vertex have influences on the displacement of this red vertex. I denote the constants for these influences by H and G respectively. And of course, the points other than this yellow vertex also have influences on the displacement of the red vertex. So we can simply sum up the influences from the from all vertices to compute the displacement of the red vertex. We can construct similar equations for the vertices other than the red vertex to get this matrix equation. Then this matrix equation is solvable by moving the unknown displacement vector terms to the left-hand side and keeping the known traction vector term on the right-hand side, and taking matrix inverse or something like that. This is basically the BEM formulation for elastostatics, but for elastodynamics, we need to consider a few more things. Let's say we want to get displacement of vertices at the nth time step. Then elastic waves propagate over a few time steps, in contrast to the elastostatics case when essentially elastic waves propagate immediately inside the volume. The natural question here is how many past time steps we need to consider in the simulation. But fortunately, the number n max is bounded by the maximum time it takes for any elastic wave to propagate from any point on surface to another. In the BEM equation, this time history effect appears as a summation over the past n max time steps. So this is the basic matrix equation for boundary element method for elastodynamics. And we simplify the notation like this. Here are a few important remarks. First, if you want to compute the unknown displacement vector at current time step n, then we need the traction vector from the current time step. And also, in addition to that, we need displacement and traction vectors from the past time steps and max time steps. second important remark is that we can pre-compute the H and G matrices here because they can be computed on the undeformed configuration of elastic body. Third, I just described the intuition behind the method, but this is formally derived using boundary integral equation formulation. And for elastodynamics problem, there is a temporal convolution computation involved. And it is very important to choose the right way to discretize the integral equation to make the method stable enough. And also in the computation of H and G matrices, there are several singularities we need to handle, and there are a lot of technicalities that is involved. And among many different discretization methods, we base our method on chance and Antis formulation because of its high stability. And we have the detailed discussion on these kind of topics on the paper, so please go check it if you're interested. So this is a brief summary of elastodynamics BEM. Still, this is not the end of the story. Our method goes beyond just a simple adaptation of elastodynamics simulation for animation, where we address a few domain-specific challenges, I would say, to design a surface-only dynamic deformable simulation method for computer animation purpose. There are three of them, and the first problem is the linear elasticity limitation. Our method is based on linear elasticity model, and it is very well known in graphics community that this model cannot handle large deformations such as rotation. And in graphics, researchers have tackled similar problem. Let's say here, for example, for FEM simulation. In this figure from Miller et al. 2004, we can observe that there is a significant volume gain on the head of the animal on the left when you apply linear elasticity model as is. But if you compute the linear strain measure for each finite element in a co-rotated frame, then we can circumvent that kind of problem. So we design our approach based on a similar idea. That is to simulate the deformation of objects with BEM inside of moving rigid body frame. And there's a difference between our method and FEM, co-rotated FEM, that we have only one moving frame per object, not per element. So that is difference. So in our method, the first step is to estimate global translation and rotation of the object given surface traction. And now we are moving the frame. That means we need to account for some fictitious forces due to the moving frame in boundary element method. This is our second step. So we augment the BEM matrix equation with additional fictitious force terms expressed in terms of the body frame acceleration vectors. So here, small b denotes body acceleration vectors, and large b denotes the influence of body acceleration to the deformation. Finally, we correct some small global displacement errors remaining in the frame by extracting the remaining global translation and rotation from the deformation vector using shape matching. This error correction step is very important to improve the stability of a method. And we designed the method very carefully to make the BEM simulation stable, even in a moving frame. Here's a result with or without our body frame update method. And in this specific scenario, we can easily see that augmenting the BEM with body frame significantly reduces the volume gain artifact. The second problem we consider is the existence of dense matrices in BEM matrix equations. Here, H and G matrix is dense, and the memory cost grows quadratically with respect to the number of vertices. And for example, if we need to use the time histories from the past 5 time steps for a model with 3,000 surface vertices, then we need 7.8 gigabytes of memory just to store the matrices, and that's not cool. And because of this, naive implementation of BEM is usually slower than other methods such as FEM. So this motivated us to design a simple matrix compression method to address the problem. So in the BEM matrices, H and G matrices, the coefficient for influence from yellow vertex to red vertex is, let's say, stored in this entry. Similarly, from the green vertex, let's say it's stored here. And if you look at the input surface mesh, 2 points, yellow and green, are very close to each other in terms of distance, and also they have very similar normal vectors. So we can kind of expect that the influences from those 2 points to the red point is very similar to each other. And because of that, we can expect that these two matrix entries are similar to each other. And that's the same even if this red point is placed at different point other than the one I showed you first. Therefore, we can expect that the yellow column and green column to be similar. And if we can reorder vertex indices in a way that these two vertices have vertex indices next to each other, then the matrix will have a smoother structure in the row direction. Similarly, rows describe influences from other vertices, and with the same vertex reordering idea, the matrix have a smoother structure in the other direction, column direction as well. And based on this observation, we designed our matrix compression scheme. We first reorder vertex indices using cache oblivious mesh layouts. Compared to the original matrices, after reordering, we can observe that the matrix structure gets much smoother. Then we apply 2D discrete hard wavelet transform to the matrix and discard small entries. We apply this matrix compression to all dense square matrices. And note that the operations we need, such as matrix vector multiplication, can be efficiently handled with this wavelet transform matrices. And here's a result with different compression ratios. We can observe almost no degradation of results with 32 times compression, but with 128 times compression, probably you observe the difference. But even with 128 times compression, if the deformation we need to handle is small, then probably it's a good choice. So we should choose a proper compression ratio depending on our computational budget and the expected scale of deformation we need to handle. So the last problem is that in previous applications with boundary element method BEM, researchers have only considered simple boundary conditions and vertex constraints. This has limited the application of BEM in graphics. So we developed a position level constraint solver that is similar to the one that is developed for FEM by Durier. So when there's some force applied on the surface, we couple the deformation computed with BEM and the global motion computed with rigid body dynamics together in our positional constraint solver. So our constraint reinforcement strategy first constructs an equation between vertex positions and the force applied on the surface. This equation is linearized, so we can solve positional constraints with Gauss-Seidel iterations. And using standard or projected Gauss-Seidel iterations, we can solve 4 different types of constraints here. Here's a frictional contact scene demo with our physics-based surface-only simulation. Bunnies are thrown to the floor with 3 different friction coefficients, and we can see the difference. Please check our paper for more details and more results. So our work shows the possibility of how elastodynamics BEM can be applied for computer animation purpose, and I'm very excited to see the future development of the method in various ways. So even though we made a great progress toward practical application of boundary element method, the computational speed and memory efficiency is not on par with other methods like FEM at this point. One possibility is to design a method such as adapted mesh refinement and matrix update strategy. And because the operations on surface mesh should be generally cheaper, probably this will be a good option. And another thing we can consider is how we can incorporate nonlinearity effect into our simulation. And if you want to perform some nonlinear simulation, then actually we need to go from surface only to meshless type method by adding some internal collocation points. But we still don't know if it's going to be a good choice or not, but we have at least another way to represent the problem mathematically. And lastly, we may want to handle other surface representations based on our formulations, including like surface that define the point clouds or triangle soup boundary with many holes on it. So there are many different ways to improve the method, I believe, and we have only started exploring the application of boundary element method for elastodynamics, and I am hoping that we can make it more sophisticated over years, just like the past development of finite element method type strategies. So yeah, this is last animation we have. Yeah, this is my first conference actually, and I've been truly enjoying the program. So I would like to thank the chairs and the organizing committee members. Questions?
So it seems that you're basically avoiding measuration would give you a smart matrix. So you avoid generating internal elements or end up resulting in a smart matrix, and you want to solve the problem on boundaries, and that results in that matrices that scale what are you want to number of nodes or elements specific. So would it make sense, or if you consider splitting the surface into maybe across like large skies into more kind of self-contained surface only puzzle mesh and magic elevation for those basically the quadratic cost would be reduced into a smaller square cost.
Yeah, exactly. Yeah. So we have actually considered that kind of case. So in our paper, we have a simulation without result with domain decomposition. So we cut a beam into a few pieces, and yeah, that way for each element, because the number of vertices will be much smaller than the original one, so we can decrease the computational cost. But one caveat here is that our constraint enforcement strategy is not designed so efficiently at this point. So if we can replace the constraint enforcement strategy with something more cheaper, then I think it will be a good choice too. And of course, if we split one object into a few different domains, then that also circumvents some linear elasticity assumption as well. So yeah, that is actually a good possibility of how we may want to apply BEM and computer animation. Thank you for the question.
Thanks for the really nice presentation and really nice results. I had a question about this Nmax parameter. This is the choice of this parameter is mainly related to the propagation elastodynamic range, right?
Yes.
So did you do any experiments to see what value this parameter needs to have based on material properties of the objects you're trying to model? I would imagine that change it depending on that material properties.
Yes. So the wave speed is inferred from the material properties like Poisson ratio. And in terms of stability, that is actually a very complicated problem. And even inside of computational mechanics community, where this kind of boundary element method comes from, there are still improvements that's going on in terms of stability. And yeah, we did not conduct detailed study on stability issues or what will be the best range of parameters or time step size. So that'll be left for future work, I would say.
And one last quick question. If you compute your rigid body mass and inertia to suspend every frame. There's a body function.
Oh, currently it's based on the initial configuration. We are using linear elasticity assumption, and that kind of infers that the deformation is very small compared to what we handle with nonlinear deformation strategies. So,
Cool. One more question. Someone back there.
Yeah, very nice talk about the results. Said the performances or is not there where it should be wondering like what is the most costly step? Is it the solve or is it the shape engine solve like the gets side of like what essentially right now is that costly right now?
So if we start thinking about the constraint enforcement strategy, the story is going to be a bit complicated. So let's say we just want to perform simulation of free-flying object. Then what we need to do is to take the matrix vector multiplication and sum them up for a bunch of series of matrices. And that is actually the most costly part, I would say, because even if you compress 7.8 gigabytes to divided by 32, the size of matrices we need to load from memory and do computation is still large enough, compared to finite element method or other more efficient method. And I would say that would be the biggest constraint we have now.
Thank you very much. It's good. All right. Thanks again.
Thank you.